roughly speaking, we have data in two different formats. We have data as numerical. You can think of it as representing some sort of quantity. And we have categorical data. And it's important that we make this distinction because depending on what type the data is, depends on what type of pre-processing, what type of transformations that we need to apply to get our data into the format, in the desired format, for our supervised machine learner to ingest. Now, we primarily focused on working with numerical data, so we saw things like standard scalar to scale our data, but let's talk about categorical data. Now, one of the things that we've seen so far is that our machine learning model wants to ingest data in a structured format, rows and columns. And not only that, it wants to ingest data as numbers. If I give my machine learning model text, it's unstructured, it's not numbers, the model isn't going to make use of that, isn't going to know how to make use of that data. Of course, when we talk about natural language processing, we'll discuss all the different steps that we need to apply to that text data to give it to our supervised machine learning model. But the concept is still there. What type of processing do we need to get such that we have this structured data as rows and columns and numericals, numbers in the data set? So in this example here for the Titanic data set, let's look at one of the columns. We have embarked. Now embarked here, we notice that the data is strings. So our previous discussion, we have to figure out some way we can transform those strings into numbers. Now what are your thoughts? How should we transform these strings into numbers? One thing we need to understand is this embarked column, it's a category. So because it's a category, we can go ahead and one way we can encode this data is we can go ahead and assign a numerical value, an arbitrary numerical value for each of the categories. For this column here, there are 3 different values for embarked, this embarked field. So we can go ahead and encode 1 to be 0. Well, let me be more clear. We can encode one of those, and this, for example, S to be 0, C to be 1, and the other one that you don't see here is Q. We can go ahead and encode that as a number Q. So let's use pandas. Pandas is a great tool for data exploration. So we'd look at unique. So using the unique method for this series, we see that we have 4 distinct values because we have a missing value. But we can go ahead and easily replace that missing value. We'll go ahead and do that right here. And call this embarked. Embarked, I'm going to just say fill NA, and we'll just go ahead and fill it with, in this case, the value S, which is the most common, and we can use pandas to figure out what was the most common category. I'll go ahead and do that. And I want the values. I want these fields as a numpy array. So if I look at embarked, now it's a numpy array of nothing but S, C, and Q. So there's that 3rd category. So yeah, so we can go ahead and create a mapping. Map S to something like 0, C to 1, and Q to 2. And this is arbitrary, and we can do this manually, of course, but since it's a very common thing we need to do, scikit-learn provides us a tool for us to do this. And guess how this tool is going to manifest itself in scikit-learn? How will it show up? In other words, is it going to be a function? Is it going to be a regressor? What do you think it's going to be? It's going to be a transformer. Let me import that. It's going to be called our label encoder. Now, full disclosure, this label encoder is really meant to encode the labels, the Y's. But you can go ahead and use it to encode your X data, your feature matrix. Let's go ahead and import it. And as we should do every time we're going to play around with a new model or new tool in scikit-learn, let's look at the documentation. It says here, encode labels with value between 0 and n class minus 1. Okay, so this is basically saying what we discussed. It's going to encode these three categories to have a numerical value, an integer. 0 all the way to, in this case, 3 minus 1, 2. Let me show you an example here, how it works. So let's go ahead and use it. So I'm going to say encoder equals label encoder. Encoder is to fit transform. Do all that in one step. Go ahead and do it in 2 steps if you're more comfortable. Okay. In this case, I've encoded my data, my label. So yeah, so we see here we have things like 2, 0, and 1. Now you might be wondering, okay, well, we can go ahead and look, right? Let's say the question might arise is, well, what was 2? What is 0 and what is 1? We can go ahead and look at the original data, embarked, and we can figure that out. We can look at embarked. I think that's what I call it, embarked. There you go. And it looks like S is 2, and C is 0, and S is 2, and that, yeah, that makes sense. But that's a little annoying. In fact, if we look at the documentation, we look at the attributes. Doesn't really say the attribute. Oh, classes, there you go. An array of shape holds the label for each class. Let's go ahead and see if that can tell us anything. Encoder classes. Notice it ends with an underscore. So this is useful. This is going to provide the mapping between the integer and the original label. So this is what it's the way to read this is that integer position 0 is going to correspond to C, 1 is going to correspond to Q, and 2 is going to correspond to S. We saw that. We saw that S corresponded to 2. And that makes sense. So we can go ahead and look at this class's attribute to see that mapping between the integer and the original string label. Now we've encoded this field. Okay, so now we can go ahead and incorporate this this data. We formatted it for our machine learning model because now we've taken something in strings, we converted it into numbers for our model to ingest and learn from. But are there any concerns with the way it's written? Or not say the way it's written, but any concerns at the moment that perhaps something that we don't want our model to do, but it might learn from or might pick up from. Remember, these models are trying to learn patterns, and we've got to make sure that we don't have any patterns that we got to make sure there's no patterns that we don't want our model to pick up on. Well, we don't want our model to pick up on something like, well, let's look at this. Let's look at our encoder in classes. So essentially we've encoded the category C to be 0 and the category 1 to be Q and 2 to be S. But we don't want our model to learn something weird, or at least for us doesn't make sense, that since Q is 1, 2 times Q is S. And something like, S minus Q is equal to C. Because we've essentially encoded a numerical value for these categories. We don't want our model to pick up on that behavior that we understand is weird, but perhaps our model isn't going to understand that. It's going to pick up on that. Also, what it's saying here, given this encoding, we're saying that our model can pick up on the fact that S is greater than Q and is greater than C. But these represent categories, and sometimes these categories don't have a natural order to them. In other words, it doesn't make sense that S is greater than Q and C. It doesn't make sense given our data. So we don't want that. That might happen if we leave our data in the current format. So let's discuss another technique we can use to transform this data into a format to prevent something like this from happening, for a model to pick up on some pattern that really isn't a pattern. And one of those techniques is called one-hot encoding. Now the way one-hot encoding works, so now let me go ahead and sketch this out. So essentially we have a category or a column where we have values like 0 and 1, 1 and 2. In this case, let's go back to our example we've been doing where there's 3 distinct values for this column. What we can go ahead and do is that we can take this and generate 3 new features. And generate new features based upon all the distinct values for this category, for this feature. Since in this example we have 3 distinct categories, 0, 1, and 2, we can go ahead and create 3 new features. And the first new feature generated will be 0 or not 0. Then the other one would be 1 or not 1. And the last one will be 2 or not 2. Let me just generate these partitions. So now we generate these 3 new features. And for this observation, since it has a value of 0, it's going to be true, since it is 0. So since this is true, we're going to use a value of 1. And since it's not 1, it's 0. And since it's not 2, it's 0. So what happened here is that when we generate these 3 new features, each observation will have a value for these 3 new features, but only one of them will have a value of 1. In this example here, I know it's a bit shifted. This is a value of 1. So since it's not 0, it's going to have a value of 0 here. But since it's 1, since this observation has a value of 1, it'll be 1 there and 0 there. Same thing here, 0, 1, and 0. And for the last observation, it's a value of 2. So these 2 columns, these first 2 columns, will be 0, but the last one will be 1. So this is called one-hot encoding. We can do that in scikit-learn. So it's from, I believe it's in pre-processing. Import one-hot encoder. And let's look at documentation. So encode categorical integer features using a one-hot, aka a one of k scheme. Let's take a look at the example. Okay, so there's our example there. So notice in this situation, it looks like there appears to be 2 distinct values, and it generated the corresponding columns. All right, so let's try that out. I'm going to call this one-hot encoder, one-hot fit and transform, and call it x of t. I did not call it x of t. Oh, I thought I did. Maybe I just run this there. Okay. Problem there was I forgot to reshape this. Okay. So this is the result of the transformation. Notice here, go ahead and call this result x of tt to differentiate between this one there. Of course, if I were to do this, I would do pipeline, so I won't have to keep track of all these intermediate variables. But for illustrative purposes, I am not using pipelines. Okay. So let's look at x of tt. And we see that it's a sparse matrix, and it's telling us how many stored elements. And yeah, so we have a sparse matrix. So what does this mean? Well, one way we can store data instead of using sort of traditional NumPy arrays is that if our matrix has a lot of zeros, then perhaps it's more memory efficient to just store the non-zero values, but also store where they occur. That's a sparse matrix. In this situation, we got a sparse matrix back. There's a method called toArray for that sparse matrix where we can go ahead and expand it out. And here it is. So since we have 3 categories, we have 3 new columns, and all those values are nothing but 0 and 1. And notice for each observation for these 3 columns, there's only going to be one value. Only one column which will have a value of 1, everything else is 0. Hence the name one-hot encoding. which makes sense because an observation, it can't be C and Q at the same time. It's got to be either one or either the three, since we have three different categories. Same thing if you're working with days of the week data. You would use something like one-hot encoding. Let's look at one-hot encoder. Let's look at the syntax. In fact, if we didn't want a sparse matrix, notice the default is true, we could have just specified sparse equals false. Although oftentimes it's best to keep it as a sparse matrix. But if for some reason you need to have a full matrix, you have that option. And now X of TT is a full matrix, is no longer sparse. Scikit-learn is, like I said, a lot of the defaults that Scikit-learn has set are a good choice. And sometimes the transformer is going to give you back a sparse matrix, and if you try to convert it into a full matrix, you might run into memory issues. You'll see that when we start doing natural language processing, so I wouldn't fool around too much with this keyword argument to create a dense matrix, a full matrix, as opposed to a sparse.